He has been awarded and has pending several patents related to nitric oxide. His discoveries and findings have unveiled many beneficial effects of nitrite in the treatment and prevention of human disease and may provide the basis for new preventive or therapeutic strategies in disease associated with nitric oxide insufficiency and new guidelines for optimal health. He discovered a safe and natural way to reduce nitric oxide, enabling the body to restore its nitric oxide function. He also commercialized his nitric oxide technology through the formation of Nooshin's lab, where he is the co-founder and chief science officer. Please help me welcome Dr. Bryan.
It's not crazy important, so you're fine.
Okay. Well, thank you very much, and howdy. So it's good to be close to home. I grew up just outside of Caldwell, near here, and then moved away, so I consider Texas A&M really a home. In fact, out of high school, I spent a year here before I transferred to University of Texas at Austin. So don't hold that against me. So what I hope to do today is really share with you some of our fundamental discoveries in the nitric oxide field that really turned out to be important in the field of human nutrition and biochemistry. And so my financial disclosures, as I mentioned, I'm a founder and shareholder of Human to the Power of N, a shareholder and advisor for Sage Pharmaceuticals, and I receive royalties on a number of issued patents from University of Texas Health Science Center in Houston. And so what I hope to do is tell you this story. So I started in this field almost 20 years ago, and this is a quote I like to use because research is to see what everyone else has seen and to think what no one else has thought. And so part of my objective today is to tell you through these simple observations that we made probably 10 or 15 years ago, how they transformed really the way we think about nitric oxide biology and really functional food and nutrition. So keep that in mind. And so my objectives are really very clear. It's to provide an understanding of nitric oxide, the role of nitric oxide in health and disease, and illustrate how certain foods affect NO production. So I think over the past 30 or 40 years, we've missed a basic component of functional foods, primarily a vegetarian diet, Mediterranean diet, that may be solely or partly responsible for a lot of the heart benefits, cardiovascular benefits, anti-cancer effects of these. And so as I go through some of the biochemistry and some of the human clinical data, I'll review then what are the safe and effective strategies, what's the human metabolism of nitric oxide, what goes wrong in people that can't make nitric oxide, and then what we've discovered to overcome these, whether it's a genetic limitation or whether it's a dietary problem and not getting the right nutrients from the right foods. So you may ask yourself, who needs nitric oxide and why is this important? And by the end of this, I'll show you data that will corroborate these statements, but certainly anybody who's aging. The older we get, the less nitric oxide we make. Anybody who's sick, certainly anybody over the age of 40, circulatory issues, diabetics, people with low energies, nitric oxide controls and regulates mitochondrial ATP production. People with sexual dysfunction, erectile dysfunction in both men and women is really the first sign and symptom of nitric oxide deficiency. I won't have time to go into it today, but anybody on antacids, proton pump inhibitors, the third largest prescribed drugs worldwide, inhibit nitric oxide production. And in fact, people who've been on PPIs for 3 to 5 years have a 35% higher incidence of heart attack and stroke because of the disruption of nitric oxide. I think from my perspective, nitric oxide is important because I think medicine has to be proactive instead of the reactive practice it's been for the past 100 years. Get ahead of disease before, because it's easier to prevent disease than it is to treat and manage disease. And athletes in the room looking to improve their performance, we can enhance human performance simply by restoring and enhancing nitric oxide production. And I'm going to present this all from a very simple concept, an age-old concept that a man is as old as his arteries. Because no matter what disease state you're looking at, it's always characterized by low blood flow, ischemia, and hypoxia. Whether it's disease of the joints, vascular dementia, heart attack, stroke, all these are characterized by low blood flow. So if we can begin to understand what happens in vascular biology, we know that through even post-mortem analysis of young people who have died in car accidents, that if you do look at their coronary arteries, they have fatty streaks and even some advanced plaque development, even in the early 20s, 30s. But depending on diet, lifestyle, and some genetic factors, you can either advance this plaque deposition along the arterial wall, or you can prevent that plaque regression. But really what's the end of the story for most people is that this plaque becomes unstable, the plaque ruptures in the coronary arteries or in the cerebral arteries, and you have a heart attack or stroke. So it's really not just the degree of occlusion in these arteries, but the stability of the plaque. So if you can stabilize existing plaque in the arteries, or if you can regress existing plaque, in the arteries, then you can protect from heart attack and stroke. Over the past 30 years, it's been recognized that you can pick up biomarkers in the peripheral blood that really reflect the degree of vascular disease. You can image this through ultrasound, but really conventional labs can pick up, if you have a heart attack, it's diagnostic for creatine kinase or troponin T. But there are other biomarkers that begin to show up in the blood of humans that reflect earlier stages of vascular inflammation, such as high sensitivity C-reactive protein and microalbuminuria. Later stages where you have vulnerable plaque, it's myeloperoxidase is upregulated, as well as these certain lipoprotein particles. We've also been able to get functional measurements of nitric oxide along this progression of cardiovascular disease. So when you lose the ability to make nitric oxide in the endothelial cells, it really sets the stage for the inflammatory cascade of cardiovascular disease. So understanding what functional nitric oxide production is, combined with routine biomarkers, we can begin to assess then patient risk for heart attack and stroke based strictly on their nitric oxide output. And despite whatever the cause is of cardiovascular disease, or no matter if it's the infinite number of insults we give to our body, the human body responds with 3 finite responses: inflammation, immune dysfunction, and oxidative stress. So it's known that if you can mitigate the inflammatory cascade, prevent immune dysfunction and the oxidative stress associated with these, you can prevent cardiovascular disease. And so I'm going to present to you ways we've been able to do that simply by restoring the function of a single molecule called nitric oxide. And so the question we asked years ago is, how do you do this? We do this very simply through this nitric oxide molecule. It's very simple. It's 1 nitrogen, 1 oxygen. It's a free radical, meaning that it has an unpaired electron in its outer orbital. And for years you probably thought that free radicals were these toxic, damaging molecules. But because of the polarity of this NO bond, this actually acts as an electron donor. But you should also appreciate in biochemistry, any electron-donating species has anti-inflammatory properties and antioxidant properties. But it has a half-life of less than 1 second. So it's produced, it's a gas, and then it's gone. It elicits some cell signaling functions, and then it's gone, it's oxidized. And it's now recognized as one of the most important molecules produced in the body of mammals, including humans. But before it was discovered that it was produced in our body, it was considered a toxic air pollutant. And it shouldn't be confused with nitrous oxide. That's the dental anesthetic you get. They sound the same, but they're completely different. There's over 140,000 papers, 150,000 papers in the published literature on nitric oxide, where it's involved in everything from maintaining the integrity of the cardiovascular system, gut motility as the non-adrenergic, non-cholinergic mediator, critically important for regenerative medicine. Nitric oxide is the requisite signal that tells our own stem cells to mobilize and differentiate to repair damaged cells. It's a neurotransmitter in the central nervous system, controls cell cycle, the urogenital tract, and it's how our white blood cells kill off invading pathogens. So when you lose the ability to make nitric oxide, a lot of bad things happen. It's not just hypertension. You get immunocompromised, you get vascular dementia. There's some cancers associated with loss of cell cycle. In 1998, the Nobel Prize in medicine was awarded to these 3 U.S. scientists for their discovery of nitric oxide. And it was Fred Murad who discovered that drugs like nitroglycerin that were used for 150 years prior to the 1970s for the treatment of acute angina worked because these drugs were metabolized into nitric oxide that then dilated the coronary arteries and get complete symptomatic relief of the acute angina. In 1980, Bob Furchtgott discovered that our endothelial cells makes a substance that makes these blood vessels relax or dilate. And he termed this endothelium-derived relaxing factor. And then it was Lou Ignarro who discovered that EDRF is nitric oxide. So the story was that if you give a nitric oxide donating drug or species, or you stimulate endogenous nitric oxide production, it would dilate blood vessels, improve oxygen, blood flow, and nutrient delivery to downstream tissues. Bob Furchtgott passed away several years ago, but it was Fred Murad who recruited me to join the faculty of UT Medical School back in 2005. So a lot of the early experiments we did were with Fred as my department chair, and then Lou Ignarro is a close friend and colleague who's written the foreword to several of my textbooks. This was the front page of the New York Times the day the Nobel Prize was awarded. That the discovery of nitric oxide and its function is one of the most important in the history of cardiovascular medicine, by Val Fuster, who was then president of the AHA. And I show you this because this is a relatively new discovery in terms of nitric oxide. So we all know that part of the cardiopulmonary respiratory system is that you take up oxygen in the lungs, you excrete CO2, and in the periphery, that hemoglobin, oxygen bound to hemoglobin, goes through this R to T transition where it's an allosterically regulated protein that offloads oxygen. Well, if you don't have nitric oxide bound to the hemoglobin, the oxygen becomes stuck, and it can't deliver oxygen to the periphery. So if you consider this in terms of critical care medicine, where you've got patients on 100% oxygen, they have 98% O2 sats, but they can't deliver that oxygen to the periphery. So they're systemically hypoxic until you fix the nitric oxide functionality of that hemoglobin. So nitric oxide is now considered the third gas in the respiratory system. And this just illustrates kind of mechanistically how nitric oxide works. So when we begin to exercise, this causes shear stress on these endothelial cells, activates an enzyme called nitric oxide synthase, and this enzyme converts arginine to nitric oxide and you get citrulline as a byproduct. That's why exercise is medicine, because it stimulates nitric oxide production. Nitric oxide, being a gas, diffuses into this underlying smooth muscle where it activates an enzyme called guanylyl cyclase. Guanylyl cyclase converts guanosine triphosphate into cyclic GMP. And it's cyclic GMP that acts as the second messenger that, through a calcium-dependent mechanism, regulates smooth muscle relaxation. This is also the site of action of PD-5 inhibitors, drugs like Viagra, Cialis, and Levitra. So these drugs potentiate nitric oxide-based signaling. They're not nitric oxide donating drugs, as most people think. But tens of billions of dollars a year in drug therapy, they only work in 50% of the men which they're prescribed. So these 50% of non-responders can't make enough nitric oxide here to activate this enzyme. So our work has shown that if you fix this enzyme here, you can take non-responders to PD-5 inhibitors, make them responders, or actually lower the effective dose of these drugs, mitigating the side effects by enhancing erectile function. And this, unfortunately, is what we're all faced with in the room. As we age, we lose the ability to make nitric oxide. In fact, 10 to 12% per decade loss of nitric oxide function. So by the time you're 40 or 50 years old, you only have about 50% of the nitric oxide you had when you were younger. So no wonder you don't perform as well athletically. Some people don't perform as well in the boardroom or even in the bedroom the older they get because of the loss of nitric oxide function. And so we asked a very important question several years ago, that if we can prevent this age-related decline in nitric oxide production, can you prevent age-related disease? Very fundamental question. So what does a nitric oxide deficient patient look like? Typically they have elevation in blood pressure, they have advanced atherosclerotic disease, thrombosis, coagulopathies, their platelets become hyperactive, Alzheimer's, vascular dementia, erectile dysfunction, any type of circulatory disease, chronic inflammation, and compromised performance, whether that's performance in the bedroom or on the athletic field. And this is the complexity of what we've been dealing with for about 25 years. Because this enzyme, nitric oxide synthase, is probably one of the most complicated reactions, biochemical reactions in the human body. It's the only enzyme known to require 8 different cofactors and substrates. And this is a 5-electron oxidation. So we take this guanidinonitrogen here through a multi-step 5-electron oxidation, generate nitric oxide. And so it's very energetically and kinetically unfavorable. So in normal healthy people, this enzyme, this reaction typically proceeds uninterrupted. But if you have high oxidative stress, if you have reduced glutathione, reduced oxygen, this enzyme becomes uncoupled and you generate superoxide, this oxygen radical, instead of nitric oxide. We've also identified that we can extend the biological half-life of nitric oxide from 1 second out to tens of minutes and sometimes hours by its ability to bind to glutathione. We've identified some natural product inhibitors of this metabolizing enzyme, and that's the basis for the Sage Pharmaceutical compounds that we're developing for airway inflammatory disease and asthma. And then I'll spend a lot of time today on talking about once nitric oxide is produced, it's oxidized to nitrite and nitrate. And we've identified bacteria that live in and on our body that recycle this nitric oxide activity. To prove to you this is important, your ability to generate nitric oxides predict how well an athlete you are. If you generate nitric oxide upon exercise, you're a superior athlete. If you take older patients with endothelial dysfunction, these are patients who are on an exercise stress test. And because they can't generate nitric oxide in their coronary arteries, they fail the exercise stress test. And these patients were taken upstairs and either undergone cardio bypass surgery or put stents in their arteries. So your ability to generate nitric oxide predicts not just how well you can perform athletically, but your susceptibility to heart attack and stroke. And so this is a very busy slide, but the point of this is to tell you that the literature tells us that loss of nitric oxide production is really the earliest event in the onset and progression of cardiovascular disease. And it's not only associated with all cardiovascular risk factors, but it has predictive value for future atherosclerotic disease progression. So your ability to generate nitric oxide tells how susceptible you are to heart attack and stroke, but also can predict when you're going to have a heart attack or stroke. So I'm going to take you through a couple of very basic science experiments we did over a decade ago that really changed the way we thought. We saw what everybody else was doing, but we thought a little bit differently. And I'm from Texas. We asked very simple questions. We asked a very simple question that if we enhance nitric oxide production in the heart, can you protect that heart from injury, from a heart attack? And then if you could we trace that phenotype biochemically to give us some prognostic or diagnostic biomarkers that would then allow us to predict future heart attack events? And so we use transgenic mice. We can overexpress the nitric oxide synthase enzyme only in the cardiac myocytes. You can see that the transfection was successful. The enzyme is active because we generate a lot of nitric oxide metabolites. And in this study in 2006, if we subject these mice to heart attacks, so we tie off their LAD way up high in their heart for 45 minutes and then reperfuse 24 hours, there's no injury to the heart. So even though it's been with no flow ischemia for 45 minutes, the heart performs just like a control. So it's extremely cardioprotective. The interesting thing we did then was look at what's happening in the blood and other tissue. So we found that the plasma levels of nitrite and nitrate were elevated. We harvested the liver of these mice and found that the liver enzymes, or the liver nitric oxide biochemistry, looked exactly like that of the heart. This was a little bit puzzling because nitric oxide can't survive transit from the heart to the liver with a half-life of less than 1 second. So some interesting biochemistry was going on here, and it wasn't overexpression of the enzyme because the transfection was clean in the heart. So then the next question we asked was, what, if anything, does this mean? So if we cut off blood flow to the liver for 1 hour and then reperfuse for 5 hours, we protect the liver from injury. So the nitric oxide produced in the heart protected the liver. This was the first description of a hormone effect of nitric oxide. So prior to this study, it was thought that nitric oxide could only act in the cell in which it was produced or a neighboring cell. It couldn't act as a hormone. So hormones are released from one tissue and they have systemic effects. This was the same as nitric oxide. And this was my aha moment because this told me that all we had to do was generate nitric oxide gas in a single biological compartment. And then this hormone effect would take care of all the rest. And keep in mind the oral cavity is the most accessible, non-invasive biological compartment we have access to. We also begin to think, well, if all we had to do was increase plasma levels of nitrite, nitrate, and perhaps affect the internal biochemistry, that we know how to do this simple through diet. Because the air we breathe is 78% nitrogen. Through lightning fixation, this fixes nitrogen. There are microbes in the soil that when you add nitrogen to soil or potassium nitrate, that these bugs fix nitrogen into usable forms. It's primarily nitrate, nitrite. So any vegetable that we eat that's grown in this nitrogen-rich environment, we're getting a source of nitrite, nitrate, or any animal that we eat that eats the grass or the vegetables, and we consume them. These are dietary sources of nitrite and nitrate that affect what we're doing. About 15 years ago, we discovered a human nitrogen cycle. So primarily through green leafy vegetables. I throw a little bacon on here because that's always good for you. But it was known since 1978 that our salivary glands will concentrate nitrate. And no one knew, cancer biologists didn't know why our body would do this, because nitrates were thought to form cancer through nitrosamine formation. But we now know that there are nitrate-reducing bacteria that live in the crypts of the tongue that reduce nitrate to nitrite. Humans don't have this enzyme, so we're 100% dependent upon the bacteria. Then when we swallow our own saliva, the pKa of nitrite is 3.4. So in the acid environment of the stomach, it generates nitric oxide gas. So I think I tell my mom all the time she was right because she said, eat your vegetables and don't spit. Because by doing this, we're fueling this nitric oxide production pathway. And then it's taken up again, and then the cycle continues. But we're also beginning to realize that 50% of the nitric oxide activity that we got came from our diet and the presence or absence of certain bacteria. So we did some basic stoichiometric measurements and found that we could basically give a certain amount of nitrate that one could get through a diet, through eating certain foods, and then not only affect athletic performance, but also lower blood pressure. And this isn't a foreign concept. The father of medicine himself, let food be thy medicine and medicine be thy food. So what is it? What is the certain component in food that allows for these protective mechanisms? And I think in food science and nutrition, you guys are looking for that every day. Is it antioxidants? Is it certain vitamins, trace minerals. Well, no one's ever looked at nitrate in terms of their health promoting effects. They've always looked at ways to eliminate it from your diet by the elimination of hot dogs and bacon. But I'll show you the regulatory ignorance on that later. But this just shows that if you give enos deficient mice, these mice can't make nitric oxide and they develop type 2 diabetes. So if you give them nitrate simply in their diet, they gain less weight even though they're eating the same amount of food, drinking the same amount of water, about a 20% reduction in triglycerides, and less visceral fat deposition. Better management of blood glucose, pro-insulin to insulin ratios improve, meaning that insulin sensitivity increases. Hemoglobin A1C, which is a more chronic marker of blood sugar control, we reduce that by about half. And then better blood pressure management as well. And so that was an interesting observation study, but it didn't tell us mechanistically what was going on. So we did a literature review and tried to find out what's going on in insulin signaling. And I show you this because diabetes is a huge epidemic and it's completely curable and preventable by the proper diet. And mechanistically, we know what happens is when insulin binds to the insulin receptor, that initiates a lot of these different kinase enzymes that phosphorylate certain enzymes. Well, a lot of these converge on a certain serine residue on enos. And so whether it's AKT, PI3 kinase, or AMP kinase, where metformin works, the #1 prescribed drug for diabetes, stimulates AMP kinase, and that phosphorylates this enzyme. But the literature didn't tell us anything after that in terms of nitric oxide. But we know that GLUT4 translocation is the terminal step in glucose uptake and internalization into the cell. So our thought process was, we know in diabetics they can't make nitric oxide. So what is nitric oxide doing to GLUT4 translocation? And perhaps you can see this with the lighting, but we engineered some cells to where you could take green fluorescent protein and co-localize it with the GLUT4 transporter. And so normally this is a cytosolic enzyme, so you can see the inside of the cell lights up. But if we stimulate this with nitrite, you can see the cell membrane start to light up. So we can see GLUT4 translocate to the membrane, enhance glucose uptake, and improve insulin signaling. We published this several years ago, but mechanistically we figured this out because there's 2 cysteine residues that have been evolutionary conserved throughout evolution of any organism that uses glucose or carbon as an energy source. They have these 2 cysteine residues. So NO can modify these, and through this post-translational modification, that's necessary and sufficient for GLUT4 translocation. So whether it's type 1 diabetes or type 2 insulin-resistant diabetes, you can potentiate insulin signaling simply by restoring normal nitric oxide function. Now here's the kicker. How much nitrate do we need? We know from the published literature we need 300 to 400 milligrams to see changes in blood pressure or improvement in exercise capacity. But the US population, the Western diet, we're only getting about 150 milligrams nitrate per day. And that's over 2 to 3 meals. So there's not enough nitrate in a bolus any given time because the production of nitric oxide from nitrate is so inefficient that you're never getting enough. So in essence, we become a nitrate deficient population. So the next question we did, and this was done in collaboration with Dr. Osborne here at Texas A&M, was we wanted to see if we wanted to recommend certain foods to normalize blood pressure, how much celery would you need to eat? How much broccoli would you need to eat? And so we did a nationwide survey. We went to, Wes did, went to Raleigh, North Carolina, New York, Chicago, Los Angeles, and Dallas. Went to the same retail grocer and bought the same vegetables off the shelf, brought it back to my lab at UT, and we measured the nitrate content of these vegetables. And this is what we learned, that, and perhaps you can see this or not, but the point here is that if you lived in Dallas or Los Angeles, you could eat about 6 stalks of celery and get enough nitrate to lower your blood pressure. If you lived in New York, you'd have to eat about 84 stalks of celery. So there's no way in hell we could ever make recommendations based on how much celery or lettuce or spinach you could eat, because it's geographic variability. And so it depends on where you live, how these vegetables are grown, time of harvest, processing, all these things you guys learn in the food sciences affects not only the nitrate availability, but also other important nutrients. The other important consideration is nitrate is inert in humans. Humans cannot metabolize this enzyme. And that's illustrated here, that if you give chlorhexidine mouthwash to normal intensive patients to eradicate the oral bacteria, their blood pressure goes up. And think about this, there's 186 million people a day in the US that use mouthwash. So I tell people it's better to have bad breath than to have a heart attack. So stop using it. And this shouldn't be surprising either, because the human genome is only 23,000 genes. The bacteria that live in and on our body provide about 3 million gene products. And these bacteria are there to do things that we as humans can't do or haven't evolved to do. So we started looking at what's growing in people's mouths. And so we did a study at the Texas Medical Center, and we got healthy volunteers, what we thought were healthy volunteers, did tongue scrapings, and then looked at these denitrifying bacteria. Because these bugs will reduce nitrate to nitrite to nitric oxide, and they can reduce it all the way down to elemental nitrogen. So what we found was, number one, there's not a lot of healthy people walking around the Texas Medical Center, but two, that if you were able to reduce nitrate, you had different oral microbiome than those that couldn't. And so they begin to cluster. These bacterial communities begin to cluster, not just in diversity, but also in number. And so we published this several years ago, and again, an interesting observation that there was an association between about 12 to 15 different bacteria in people that were good nitrate reducers and people that were lousy nitrate reducers. So we followed that up in another study, and this is unpublished. We've been trying to get this published for a couple of years, but it's a little bit disruptive, and hopefully you'll appreciate that. So we took normal, healthy, young, normotensive patients, did tongue scrapings to figure out what they had growing in their mouth, give them chlorhexidine mouthwash twice a day for 7 days, see what happened to their blood pressure, and then also see what it did to the bacteria growing in their mouth. Didn't change anything else, didn't change their diet, didn't change their oral hygienic practices. This was the design of it, but this was kind of the first look at the data. And you can see some people's blood pressure went up, some people's blood pressure went down, but 7 days off the mouthwash, the bacteria seemed to normalize to where it was before. So these colonies and ecology in the microbiome is pretty resilient to stringent antiseptic. But we had some outliers. This was a 21-year-old dental student, and 7 days of chlorhexidine mouthwash made his blood pressure go up 26 millimeters of mercury. So we took a young, healthy, normotensive patient and made him clinically hypertensive, where he could be prescribed blood pressure medication in 1 week by giving mouthwash. So we looked at see what bacteria disappeared at what time his blood pressure went up and what bacteria reappeared at the time his blood pressure normalized. And then through a full metagenomic analysis, looked at what enzyme products, what protein products these bugs were expressing. So we had to unblind it. We go, what in the hell is going on with this kid? So then we modified the IRB to figure out what they were doing. Most people brushed their teeth, which is a good thing. Some people flossed, but some people were cleaning their tongue with a metal tongue scraper. And so we modified the IRB. We got a little bit more information on the subjects that were in the study. These are 84 subjects. And we could correlate their change in blood pressure with the number of times they clean their tongue every day. So if you clean your tongue once or twice a day and you took chlorhexidine mouthwash, your blood pressure would severely go up. So then we lit a little bit further and found, okay, in these patients that experience the increase in blood pressure, what is it doing to these nitric oxide metabolizing bacteria? And this was the money slide. We could predict your steady state blood pressure in response to blood pressure from chlorhexidine by the presence or absence of 4 bacteria. The number and diversity of these 4 bacteria. And I could predict your steady state blood pressure and your response to antiseptic mouthwash. And of course, everybody in here has a different microbiome, not just in the mouth, but the gut. And so this is affecting the health of many different organ systems. So then the next question was, can we overcome this variability of nitrate reduction? And so what about nitrite? Humans can metabolize nitrate. You don't need bacteria to do this. And so we put mice on a low nitrite diet, and then we gave it back in the drinking water, what we excluded from the diet. And you can see here you can decrease the nitric oxide biochemistry in the plasma in the heart. And then if we subject these mice to acute MI or give these mice a heart attack, you can see that the mice who aren't getting enough nitrite in their diet have about 40% more infarct in the heart. 50% of these mice don't survive out to 24 hours. So it's sudden cardiac death in these mice. But if we give the nitrite back in the drinking water, 100% survive out to 24 hours. There's hardly no infarct in the heart. The heart looks completely normal on echo. But that also got to thinking a little bit backwards, because once you have a heart attack, it's in humans at least, it's really years of bad habits, bad diet, and plaque deposition and then plaque instability and rupture. But it's also known that that the first stages in this are when white blood cells start sticking to the lining of the blood vessel, they migrate through, and they cause this immune dysfunction. They become oxidized, your immune system attacks these fat cells, that's what develops the plaque. The plaque becomes unstable and it ruptures. But it's also known that if you can inhibit that inflammatory pathway, you can inhibit cardiovascular disease. So this is real-time intravital microscopy of a blood vessel of 6 weeks on a really bad diet. Well, it's playing on my screen, but it's not playing here. Let me see here. Well, if it were playing, what I can see is that these monocytes and neutrophils, you can see it here, these are stuck to the lining of the blood vessel. There are a number of cells that have migrated through, but this is a heightened state of vascular inflammation. If you give that same atherogenic diet, but you put a little nitrite or stimulate nitric oxide production, you can see, obviously the blood vessel is more dilated, but if the video were to play, you can see that these monocytes and neutrophils roll along the endothelium, but they don't stick and they don't migrate through. So you can completely suppress the effects of a really bad diet simply by getting a source of nitric oxide. So then that's got us thinking about commercialization of this. Could we standardize some technology that would give the amount of nitrite and nitrate that one could get from a normal diet, provided they had the right bacteria? So the first question we have to ask ourselves, is this what nature intended? So what are the consequences of inadequate nitric oxide production, and what are the consequences of insufficient nitric oxide production? And are there populations that represent these scenarios? And we found the answer in people living in Tibet. So I was working with an anthropologist at Case Western, and this lady was interested in how these people that live at 12,000 feet above sea level work and function normally. Because if we ascend to high altitude, we get acute mountain sickness, sometimes pulmonary edema, and people die up here on Everest. But these Tibetans, they're the Sherpas who lead people up the side of Everest. So as we started doing blood flow measurements in these individual people, and the partial pressure of oxygen at that altitude is very low. So they're breathing in less oxygen per inspiration, but yet based on blood flow studies, they're delivering more oxygen per unit time throughout their body. So how are they doing this? Well, obviously they're doing this because they generate a lot of nitric oxide. So this is the EPR signal of NO bound to hemoglobin. See in the US, these are people in Cleveland and Houston. And then in Tibet, they have this real strong EPR signal. Their plasma levels of nitrite and nitrate are about 50 times higher than people living in the US. We analyzed their diet. They weren't getting it from their diet. They eat a very simple diet. They drink a lot of beer. There's no nitrate in beer. And so they're basically stimulating their own nitric oxide production to account for the low oxygen. The next answer came in hemodialysis patients. Had a nephrology colleague of mine who was been dialyzing patients for 40 years. He says, Nathan, even though I normalized all their risk factors, he goes, 70% of my patients die in 5 years. 70% 5-year mortality. So the question was, what's going on with hemodialysis in the nitric oxide production? So we did a very simple study. We took patients coming in for hemodialysis, took blood out of their fistula before they started, and then one pass through the machine, we took blood again coming out of the dialysis machine and measured nitrite nitrate, and then 4 to 5 hours later, after full hemodialysis session, measured their plasma levels of nitrite nitrate. These are water-soluble anions, so this really wasn't that surprising. But you're removing about 60 to 80% of plasma nitrite nitrate through every hemodialysis session. And so these patients get dialyzed every 48 hours for a period of weeks, months, years. They have poor endothelial function. Their diet, some of these people are eating pimento cheese sandwiches and potato chips as we're dialyzing them. So they're getting no nitrate from their diet. And doing this every 48 hours just kills the cardiovascular system. The other interesting thing was we measured their saliva before and after, and about a 95% reduction in salivary levels of nitrite nitrate. This is my 9-year-old now. So when he was born about 9 years ago, we were in the hospital. The discharge nurse was telling us to go home, and my wife's breast milk hadn't come in yet, so they gave us this whole bag of formula and told us to go home. If the milk doesn't come in, then give the baby the formula. So of course, I'm a little bit interested in what the difference is. So after a bit of a struggle, I convinced my wife to come to the lab when we left the hospital and give me some of her milk, and I compared it directly to what was in the formula. And this was a little bit shocking because the breast milk that we got, and this was colostrum, so I only had a couple of drops. But the nitrite in the colostrum was higher than any biological tissue or sample would ever measure, including any food. And this is nature's most perfect food, coming directly from the breast milk. And the formula had barely any detectable levels. So I went and I got an IRB approval. We measured 75 nursing mothers at Memorial Hermann Hospital in Houston. And what we found was that nature's really developed a beautiful system, because babies are born sterile. There's no bacteria in and on their body. So what happens in this early stage of colostrum, the breast milk delivers nitrite, because nitrate, you don't have the bacteria, the baby doesn't have nitrate reductase enzymes, so it delivers nitrite. As the gut begins to colonize, about 3 to 5 to 7 days, then the breast milk shifts from providing nitrite to nitrate. And so then the baby can metabolize it because you've got full bacterial colonization. The other interesting thing, and I don't have time to show you today, but patients born with necrotizing enterocolitis, premature babies born with underdeveloped lungs developed necrotizing enterocolitis, still about a 25% mortality. We can completely overcome necrotizing enterocolitis simply by giving nitrite in the formula. It can completely protect the gut and decrease mortality. So let me just end. I'm going to go quickly through this because we've got about 15 minutes. Then can we harness the therapeutic potential of this? And so we've developed a system whereby we can stimulate nitric oxide production from arginine. Nitric oxide is oxidized to nitrite. You can get nitrate from green leafy vegetables. We've identified the oral bacteria that do this. But about 10 years ago, we discovered that mammalian systems are really inefficient at reducing nitrite to nitric oxide. So through my drug discovery program at UT, we identified some natural product chemistry that turns that 0.1% efficacy into about 90% efficacy. Now we have a very simple system where we can generate nitric oxide upon demand along the physiological oxygen gradient under any conditions. Whether you're an anaerobic athlete, you run out of oxygen, we can turn nitric oxide on, even under low oxygen. But getting back to more than that, we know Linus Pauling tells us that many diseases can be traced to nutritional deficiency. So the question is, are we deficient in these basic nutrients found in certain vegetables? I'm a vascular biologist by training, and so hypertension is a huge problem. 2 out of 3 Americans have pre-hypertension or hypertensive. 50% of those that are given prescription medications are unmanaged. The SPRINT trial last year shows us that if you do a better job of lowering blood pressure, you reduce all-cause mortality. So we have to do a better job at managing blood pressure. And if 50% of the nitric oxide we get from the bacteria, there's no prescription medication that's targeted toward the oral microbiome. So perhaps that's the reason 50% of the people are unmanaged. And so what we've developed is a way of standardized nitrite nitrate in functional foods and dietary supplements that overcome the body's inability to generate this, whether it's through endothelial dysfunction or oral dysbiosis or even patients on proton pump inhibitors. But safety first. So there are known toxicities of both nitrite and nitric oxide. These are methemoglobinemia, that will oxidize the hemoglobin of red blood cells, and hypotension, causing low blood pressure. We know through studies in mice that the LD50, the lethal dose, is about 2 grams in normal humans. The other long-term problem is this formation of N-nitrosamines, but you can completely prevent this through the addition of vitamin C or other polyphenols or erythrobate. So again, this is no different than vitamin D or magnesium. The difference in that is you can measure those. If you go get your blood drawn, you're low in vitamin D, we take vitamin D to restore your levels. With nitric oxide, there's not those standard labs. So what we want to do is if you're deficient, we want to give back what the body's missing. So we got to know how much the human body makes in 24 hours. And we've been able to quantify this, so it's really about 20 to 40 milligrams per day. And we know how much the Western diet provides through certain foods. So this is the technology I developed at a UT Medical School in Houston almost 10 years ago. I've got 9 issued U.S. international patents on this, and we've commercialized this back in 2010. But really, this takes the underlying biochemistry and mechanistic insight that we've learned over 20 years and put it in a way that generates nitric oxide gas. So what are the clinical results of that? These are peer-reviewed, published clinical data. You can see that it generates nitric oxide gas. This is the double-blind, placebo-controlled crossover study looking at unmedicated hypertensive patients, but looking at the ultrasound of the carotid within 10 minutes, blood pressure after 20 and 60 minutes, pulse wave analysis, how stiff the arteries are after 30 minutes, and then 4 hours later, what did we do to endogenous nitric oxide production? These are the data here published in 2014. 20 minutes after this NO lozenge, we reduced blood pressure by about 6 millimeters of mercury, both systolic and diastolic. The best response you get to prescription medication is about 4 to 5 millimeters of mercury. 4 hours later, we stimulate endogenous nitric oxide production by 15%. The higher the blood pressure, the bigger the effect. In fact, if you have normal blood pressure, it doesn't further reduce your pressure, meaning that we're along that regulatory range of nitric oxide production. This is the left common carotid, so this is the blood vessel that goes up the neck. You can see internal luminal diameter, 0.52 centimeters. 10 minutes later, we've opened up that artery by about 13%. If you apply simple laws of hemodynamics, that translates into about a 34% increase in blood flow. Vascular dementia patients get better because they're hypoxic in the prefrontal cortex. This is looking at pulse wave analysis. Total vascular resistance goes down and arteries become more flexible, less stiff. The next trial was in pre-hypertension. So these are blood pressures between 120 and 139 systolic, 80 and 89 diastolic. But 95% of these patients become hypertensive within typically a year. So we thought we could reverse this trend. And this from 2015, we took 37 pre-hypertensive patients in 30 days, made them normotensive. To the tune of about 12 millimeter reduction systolic, 6 millimeter diastolic, 6-minute walk test improved, their functional capacity improved, and their quality of life improved. And if you compare this to the DASH diet, the dietary approaches to stop hypertension, the DASH diet reduces blood pressure by 5.5 millimeters systolic, 3 millimeters diastolic after 6 months of really compliant diet on the DASH diet. We do this 12 millimeters and 6 in 30 days. And then let me end with a very, probably most gratifying thing I've done, because there was a pediatric patient that has an inborn error in metabolism. And these kids will usually die at 7 or 8 years of age without a liver transplant. But they're born without an enzyme called arginose succinate lyase. And so they have a urea cycle problem, if you remember back from basic biochemistry. So their number one problem is hyperammonemia. They can't clear ammonia or nitrogen from the system. But even though they're treated for the recurrent hyperammonemia, they still develop liver failure, coagulopathies, hypertension, and renal disease. So we started looking at, we modeled this in mice, and we published this in Nature Medicine back in 2011. But we basically discovered a new protein complex that tells us a lot about nitric oxide regulation. I don't have time to go into it, but these patients that don't have this enzyme, the nitric oxide protein complex falls apart and they can't make nitric oxide. So it's a very good genetic model of nitric oxide deficiency. But here's what we're able to do in genetic patients that can't make nitric oxide. You can see at 5 years of age, this kid was put on standard pharmacotherapy, was unmanaged hypertension. At 15, and this was February of 2010, he presented to Texas Children's in the Pediatric Intensive Care Unit. His blood pressure was 185 over 130. When we saw him, we knew it was a nitric oxide problem, so gave him isosorbide, which is an organic nitrate. Blood pressure lowered within 4 days, sent him home. But he developed tolerance to these drugs. And he came back February of 2011. His blood pressure was 185 over 115. We gave him our nitric oxide lozenge. His blood pressure within 4 hours was 135 over 80. And this is what happened to his heart disease. He had severe left ventricular hypertrophy. Within 6 months, his heart had normalized. His renal function had improved. So we completely remodeled his heart, normalized his blood pressure, got him off all prescription medications, and he graduated high school a couple of years ago. And then this is one last, looking at plaque regression. We see in patients with stable carotid plaque, 6 months, we see 11% plaque regression. Cardiologists want to give everybody statins. Statins reduce plaque by 2.7% after 5 years. So let me just go through this very quickly. Obviously, there's lots of steps in this pathway. If you don't eat enough green leafy vegetables, if you don't make enough saliva, if you use antiseptic mouthwash or antibiotics, you decrease the nitric oxide production pathways. But I want to get to the regulatory issues here. But I think part of what we're trying to do here is establish dietary guidelines for this, because I think it's clear that we can fit within this recommended daily allowance in the upper limit, and we can do this with avoiding any toxicity whatsoever. The issue has always been nitrosamines, and you guys from the meat scientists probably know that nitrites is necessary for food safety to inhibit botulism, all that. But in the 50s, it was found that nitrite can form nitrosamines, which then cause cancer. But you can mitigate these because it's only secondary amines. It can be inhibited by vitamin C, E polyphenols, which are inherent in vegetables. There's little or no secondary amines naturally present in food. So let me just get to the regulatory ignorance here, because this is what I want to leave you with. But the accepted daily intake for nitrite really is 3.7 mg per kg or 0.07 mg per kg. So that only gives us 220 milligrams of nitrate per day. That's not sufficient to elicit a nitric oxide response. Same with nitrite. And we modeled this. If you look at the DASH diet, the Japanese diet, even the Mediterranean diet, which you exceed the ADI by orders of magnitude. So it tells us that epidemiologically, the diets that are known to be cardioprotective, longevity extending, exceed the ADI. And the bad diets, including the Western diet, there's not enough nitrate in there. And I think I want to end so we can have some questions. And here just puts it in comparison. So the nutritional epidemiologist told us to avoid bacon, but eat our spinach. If we eat our spinach and avoid bacon, we're getting much more nitrate and nitrite from the spinach than we are the bacon. In fact, cured and processed meats only account for about 5% of the total burden of nitrite and nitrate. So let me just conclude. Why is this not? Well, I'm stuck. But I can stop there and actually I can take questions if you'd like. But thank you much for your attention.
Thank you, Dr. Bryan, for sharing great findings. We have 10 minutes for questions.
Yes, ma'am.
So I was really fascinated by the breast milk data, the colostrum. Did you continue that any further past the initial stage with breast milk changes over time?
Yeah, we did. If you look at that, so we take the colostrum is usually the first 3 days, and it's a transition milk for usually the first week, and then you get to a mature milk stage. And that transition takes place between the colostrum and the transition milk. So mature milk is typically almost all nitrate and hardly any nitrite. Yes?
Okay, so you had mentioned L-citrulline, and there was actually something that came out in the popular press in about 2009. Dr. Patil, who works in fruits and vegetables here, he had done a study on L-citrulline as an amino acid found in watermelon. He just gave some watermelon juice, and basically said it was, helped with vasodilation, was like a natural form of Viagra. It doesn't work in the same way as Viagra does, but it's a natural. It does the same, has the same effect as far as the erectile dysfunction goes. So it's been a trend for people actually to supplement with L-citrulline. Was that something that you would recommend? Like they just take
No, so in terms of, it's certainly not a Viagra mimetic, because this, you have to, so if you give citrulline, what these partial urea cycle enzymes do is convert it to arginine. And then through that molecular complex that we discovered, it's that arginine that comes from citrulline that goes to make nitric oxide. And then you get citrulline as a byproduct. So it's this intramolecular shuttling through this complex. And so if the enzyme, and for people with erectile dysfunction, this enzyme is dysfunctional. So you can give citrulline, arginine till the cows come home, but you're never going to get a nitric oxide effect from it. So it's like putting gas in a car with a blown up engine. You have to fix the engine. And so citrulline and arginine can be the fuel, but the engine is the nitric oxide synthase enzyme. So you got to recouple that enzyme. And we've been able to recouple that enzyme. Yep.
You were saying that you all measured the nitric oxide production in Tibet, and that they produce more oxygen because of the more nitric oxide because of the lack of oxygen.
Right.
Is there any studies to see if, like breathing exercises or try maybe like a reduction of oxygen intake could actually stimulate?
Yeah, so there's a couple of examples. So the highest concentration of nitric oxide synthase enzyme is found in the airway epithelium. And if that enzyme is functional through deep breathing exercises, you can stimulate the production of NO in the airway epithelium. But if that enzyme is dysfunctional, you're never going to get a nitric oxide produced. And the other thing is you can mimic that too. It's called ischemic preconditioning. And so if you occlude the blood flow of the forearm for like say a minute or two, then reperfuse and do that repeatedly, it gets your body used to a low oxygen environment. In a low oxygen environment, it upregulates nitric oxide synthase activity and expression. So you can do that. In fact, that's why anaerobic exercise is good, because it gets your body used to a low oxygen environment and it's protected from a heart attack. Yeah.
liver protection. So does the nitric oxide also has protective effect on any other liver damage like alcohol-induced damage or hepatitis-induced damage, or just age-associated liver damage?
Yeah, the only thing we've looked at is ischemic-induced reperfusion injury in these ischemia reperfusion models. There may be some, I think there's some published data on non-alcoholic liver disease. We know we can protect the kidney as well. So we typically look at the heart, liver, and the kidney in these studies. But other models of disease we haven't really looked at. But there may be some published studies out there. You, ma'am?
Should the supplements be actually approved and be commercially available to increase nitrite production? Is there a potential issue with over-supplementation by the public, and what potential consequences would that entail?
Sure. So we addressed that back in 2008 when I went to the FDA. And how do we do this? I was trained as a drug discovery chemist, so we were trying to develop drugs out of this. But because of the natural product chemistry, we weren't creating anything synthetic. We were just isolating some natural product chemistry. So they told us we could bring this to market as a non-drug dietary supplement. The metric is 100 times less than the toxic levels. So if somebody eats 100 times this, bad things are going to happen. If you eat a whole box of Tylenol or aspirin, bad things are going to happen. So you have to have some consumer confidence that they're going to follow the directions for use. But really the acute toxicity, as I mentioned, is methemoglobinemia and hypotension. So if you take, and typically the hypotension will occur before any signs of methemoglobinemia. But when taken as, and here's the problem we face is in athletes, particularly competitive athletes, if they think 1 is good, they think 10's great.
Well, yeah, that's
And so you have to avoid that.
looking at
Yeah, but we've addressed that because I think it's important. But I think, again, you guys in the nutrition science, especially students that are going to go out, I think we have to speak with one voice and really get this out there, because it's not, the physicians typically don't want to hear this because it's a little bit disruptive. Nutritional epidemiologists were basically shooting holes in their theory of nitrite and nitrosamine for the past 40 years. They don't like to hear it, but I think the evidence is indisputable in terms of what the benefits you can get and the right amount at the right time.
Yeah, we measure already for 20 years the endogenous NO production with stable traces. So
Yep.
we have a lot of that type of information. And I'm really wondering, how does it relate to the endogenous NO production? Does it reduce the endogenous production, or is it not affected? And also the order of magnitude of the endogenous versus what you give.
It's a very good question, and so we thought about that years ago, because it's kind of like testosterone. If you give exogenous testosterone, you shut down endogenous production. This is dose dependent. So if you give a lot, you'll actually shut down endogenous nitric oxide synthase production. If you give along 300 to 500 milligrams, it'll actually stimulate endogenous production. So there is a sweet spot. We know too little is bad, too much is bad, and so there's a certain sweet spot that you can balance that at, promote endogenous production of NO, but feed this exogenous dietary supply as well.
Is there any evidence or any studies published on the importance of nitrite or the nitric oxide preventing or in the prevention or treatment of any other specific cancer or other health complications?
We published, I guess probably in 2010, nitrite specifically on metastatic colon cancer and breast cancer lines. And at certain low doses that you can get through here, it actually inhibits cancer cell proliferation and metastasis. But the higher doses, if you get up to 100 micromolar nitrite, it'll actually promote metastatic cancer proliferation. But if you have 100 micromolar plasma levels of nitrite, you're feeling awful, you're hypotensive, you get methemoglobinemia. So you can't eat enough spinach to get levels that high. Yes, sir.
You talked about the half-life of nitric oxide being about a tenth of a second, and then you saw the I guess it was the endocrine hormone response for nitrates in the nitric oxide in the heart possibly affecting the liver. When you talked about the oral bacteria creating nitric oxide in the stomach, do you see that same hormonal endocrine response, or how's it overcoming that, you know, tenth of a second half-life production in the stomach to be able to be beneficial throughout the
That's
body?
a good question. So we haven't changed the physical chemistry of NO somehow magically. NO gas itself still has a half-life of about a second. You can extend the biological activity of the nitric oxide by oxidation to nitrite, which if you give nitrite IV, you have a half-life of about 110 seconds. If you give it orally, you have a half-life of probably about 120 minutes. Also, NO binds to glutathione, and the half-life of glutathione is several hours. So there's a hierarchy of these metabolites that extend the biological activity. And you can do this simply by generating nitric oxide in the oral cavity or giving inhalative NO therapy. Yes?
So you established towards the beginning that the levels of nitrate really varied on location and a lot of other things. And so I had a kind of a two-part question. The first one was, I may have missed if you established that there was a difference between organic and non-organic. And then the second part of the question was there anything you guys found that could be done by farmers everywhere to perhaps increase it overall so that just the food production as a whole would have higher levels and that way you wouldn't have to take supplements or anything?
Yeah, so we did measure conventionally grown versus organically grown. The variability from the organic grown was even much higher than the conventionally grown. And typically there was less nitrate in the organically grown because you're getting the benefits of no added herbicides and pesticides, but you also they don't allow nitrogen, or they typically avoid nitrogen fertilizers. There's less nitrogen in the soil, less nitrogen the vegetables accumulate in the form of nitrate. Yeah, there's a whole field of agronomy that tries to normalize soil conditions to enhance nutrient uptake in vegetables. There's probably ways you can do that through rotational farming and grazing and just replenishing the soil. I think farming practices today, because they're so commercial, you're depleting everything out of the soil and new growth season, and soils are depleted of a lot of things: magnesium, zinc, selenium, nitrate. It would be a monumental effort, but I think there has to be, I mean, we do this on a pretty large scale now. We're probably the largest supplier of beets of anyone in the U.S. So we normalize the growth conditions of that to get a standardized amount of nitrate so that the finished product is what we say it is. Yes?
So most of the studies have seen until now, like study to reduce nitric oxide levels for preventing inflammation. So is there like a circulating amount of these radicals which is required, wherein like, okay, until this level it's protective and after this level it becomes inflammatory or something?
Well, oxygen radical production is part of our immune response, and so it has to be localized. And so in these local environments, and typically it's mitochondria, NADPH oxidase, and uncoupled NOS, which is the three main sources of superoxide and oxidative stress. As long as it's localized to that, and you don't have this chronic inflammatory condition where it's generating superoxide chronically, then that's part of our body's adaptive response. It's when it becomes chronically and unregulated that bad things happen.
Thank you so much, everyone. We're out of time. You don't have time
Thank you.
for more questions. Dr. Bryan.
I think we have lunch for the graduate students over in Kira Mattel. If y'all have more questions,
It's locking up on me.
y'all can resume then.
Thank you for the talk, sir.
Hey, thank you.